Today we are going to do section 7.4, area and arc length in polar coordinates. Now how will we calculate the area, that is, do integration, but if something is in polar coordinates? Well, the way we do it is, we do let's see. So what happens is first we need to calculate the area of a sector. A sector is a chunk, it's like a slice of pie. You have a circle, right? Let's draw a circle. This is on the following page, where you have a sector that has angle theta. And the question is, well, let's say this thing has a radius r, of course. Now, what's the area of this thing? Well, the area of the whole thing, of course, is pi r squared. That's your entire pizza. And then what's the slice? What's the area of the slice? The slice would be theta over 2 pi, because the whole thing is 2 pi, right? And then just your angle in radian is just theta. So the ratio goes like this. So the area equals to, why do I have 1/2? Let me see. What am I talking about? Never mind. I mean, there's a 2 here. That's why it's 1/2. So the area equals to 1/2, okay, r squared theta. You see, your pi cancels out, and that's why, and that's the area of, in general, of something called a sector, I believe, and or a slice of the pie. Now that we know what a sector is, we are going to pull this trick, okay? The area then, we are going to draw some graph in polar coordinates, and we're going to calculate the area in small slices. So we're doing the Riemann sum, but in the past, all our Riemann sums are rectangles, right? But now we're going to do the Riemann sum, but in sector form. In other words, if we have some, let's look at the previous page, okay? If we have some graph, all right, like that looks, I don't know, something like this. Here's a graph. And we're supposed to calculate the area. We're gonna do it like this, okay? We're gonna go from the graph to the origin, like that, a small slice, and then we're gonna draw the sector. This is not straight. This is round. In other words, it's part of a circle, okay? And with the tiny angle in here, and we'll call our angle delta theta, and then and then do this and slice this graph that we're trying to calculate area in, just like the Riemann sum. We'll slice it into n sectors. Okay, so you have more of them doing. They're all very small, right? And so on until you have n of them. So let's go back to the page where it says, so what is the area then? Then the total area, I mean, you add up all your slices. Each one, of course, is 1/2, okay? And the angle is delta theta times the radius. The radius is given by here's your formula, r equal to f of theta. So the delta theta, excuse me. Delta theta is the same because we're slicing it into equal parts. And then, but the f of theta, it depends on each angle. So it becomes f theta I, and then squared. So this is the theta r squared business. This part is just r, okay? And then the whole thing is squared. And let's put another parentheses here just to be clear. Okay, so that whole thing within the parentheses is the r, the radius, and then you multiply by delta theta, divide by 2, and that's the area of your one slice. And now we're gonna do the Riemann sum, which is add it all up. Okay, so the area equal to the Riemann sum, which will go from, I goes from 1 to n. N is 5 or 5 billion, right? As n gets bigger, then your slices get smaller, so your approximation gets bigger. And then we'll take it to infinity. So let's write down, as n goes to infinity, then this formula becomes 1/2. So A equal to the integral, well, don't forget the 1/2. Never forget the 1/2. It's important because it was here before and it cannot go away. Okay, from some angle from alpha to beta, these are the angles. Okay, you're integrating from here to here. And anyway, so alpha to beta, and then r squared, all right, which is f theta squared, because r equal to f theta, the whole thing squared, don't forget that, and times the delta theta becomes d theta as definition of the integral. So that is the area of how you calculate polar coordinates. Now this part in here can either be written as f theta squared or just r squared, depends on your situation, where r is in terms of theta, of course, because that's the definition relationship between r and f theta. Well, they're the same. So if you look at the bottom of the page, we're on page 663, and that is how the area is defined. Now you notice that this is, as I mentioned before, I want to emphasize on the fact that this area is not done as the Riemann sum. That is, it is not the area under the curve. It is the area from your point all the way here. In other words, it's the area made out of a bunch of pie slices. Now that matters a lot, because then when you do calculate the area, you know what you're talking about. For example, let's consider this thing. Okay, this is part of a circle. The part of the circle, let's call it, this is r equal to 2 sine theta. From, I don't know, 0 to pi over 4. Okay, theta going from 0 to pi over 4. All right, now in that case, let's say we integrate the area following this formula. Then we're integrating from 0 to pi over 4, and okay, I'll write it out, right? So we calculate the area equal to, from 0 to pi over 4, following this thing, 1/2, don't forget the 1/2, and then r equals to f theta, this thing right here, 2 sine theta squared, and then d theta. And so that will give us the area. But what area is that? It is not the area under the curve. So what are we talking about? What we are talking about is, you imagine from 0 to pi over 4, these are the points on here, okay? As theta increases, this thing crosses like this, and it stops here. This is 0, that's pi over 4. Now, so what the area is, each dot you imagine going back to 0. This is called the radial. It spells R-A-D-I-A-L, I believe. In other words, it's the line that emanates from the origin. So you imagine this thing, these are your slices. It keeps going up. My lines are not quite that straight, but you get the idea, right? So this thing right here is what you're integrating, okay? Not the area under the curve. It's this thing. So when you integrate, this is the part you're getting. So when you do integration of polar coordinates, your mind has constantly imagined your point shooting straight back at the origin, and the entire, imagine every single point shooting back, okay? And the path that it occupies, see, that's the area you're integrating, and that's very important, so that you don't think there's this part, because if you think it's this part, then you're way off, and your answer is completely wrong. So anyway, that is the area bound by a polar curve. Anyway, so what? Anyway, so that's our area. That's good enough. Let's go to the next page. Next page, example 16, which is find the area of one of the petals defined by this thing. So here is a rose, I believe. See, here's your rose, which is defined by, on the following page, example, 16. So r equal to 3 sine 2 theta. Okay, so the rose is going around and around, and you notice that it has 4 identical petals. And what do you need to do? You need to figure out the area bound by one petal only. Then what you're gonna do is calculate. Well, you don't need to calculate. You just punch into in the graphics calculator, type this exact thing in. Okay, the r equal to 3 sine 2 theta into decimals, it doesn't need to be the special polar one. It just the regular decimals, it'll recognize it. And theta is spelled T-H-E-T-A. So once you type that in, this thing will pop out, right? And then you adjust T to figure out where it ends with one petal, and probably being that it has 4 petals, I don't know. It goes from, okay, it says so. It's sine 2 theta, so it goes a little faster. Well, whatever. You just adjust the T until you realize it only draws 1 petal. And so that you know where are we stopping. And in this case, it's from 0 to pi over 2. All right. So then you integrate that part, and once you just need to figure out, in other words, what are the limits of integration. Once you've figured that out, then you just perform the integration. Okay, let's look at the next page, which the book struggled with, doing integration the hard way. This is by hand. Well, as it turns out, this isn't a very hard problem. What are we integrating? Sine squared or something? Yeah, which isn't so bad, especially there's a half angle formula or double angle formula that you can convert it into cosine and stuff. Or let's just pull this formula right out of the back, and then and don't have to worry about half angle or any other angle. And then you come up with the answer if you don't mess up any of these numbers. So so that's that, and you come up with an answer. So please do example 7.16 as part of your homework. Next, let's look at example 7.17, where we are supposed to calculate the area between 2 polar curves. Yeah, I mean, like you didn't see that coming. The first thing we do when we figure out the area is calculate the area between 2 things, right? Now, there is no difference between doing this and doing the old way, except that you have to pay attention to this principle. That is, you have two polar curves, right? And then you're supposed to find the area in between. So you do subtraction. But exactly what are you subtracting? That part is important. So if in this case, we're doing a circle like this, right? The circle is sitting on the origin. And then some other curve that goes like this. And we're looking for this area, which is fine. But what you're subtracting is, of course, you're going to figure out what this point is and what that point is, and then integrate and all that stuff. But remember what you're subtracting. You are subtracting from here. That is, you are subtracting the fan area, this whole part. If I draw it over here, okay? You are subtracting this whole part, the big one, okay? And then subtract it by the small one. Right? If the big one subtracted by small one, which equals to the moon-shaped object. So that's very important that you see exactly what you're subtracting so that your answer come out correct. So that you're not just blindly doing, oh, let's subtract and don't even know what's happening. So this is exactly what you're subtracting, which in this case happens to be just this, okay? In other situations, you might not, the subtracting alone might not work at all. You might have to add or some other situation. The point is you have to pay attention to this very carefully, because the area is defined by every single point you're subtracting, right? Going straight down to the origin, okay? The radial, remember radial, the radial area we're talking is what we're summing when we do this integration. So you actually make sure you know what area am I calculating here. So once you figure that out, then you figure out the 2 curves. There are 2 curves. Figure out what these points are by solving for some equation and solving theta or something. Yeah, probably solving for theta. Well, and then do your calculate this one, then subtract it, and then you get the right answer. Now there is one point that you have to mention is sometimes, let's see, where does the book mention it? Okay, now let's go to the bottom of the following page, page 666, where it mentions an interesting point. That is, in this particular case, you will be able to find these 2 points just fine by setting stuff equal to 0 and solve for theta, etc. But this point, the 2 points also, the 2 graphs also intersect, okay, as you can see in the graph itself, because this thing go down like this, right? or something like that. But you will not be able to solve for this because, well, that's just, the reason is because the polar coordinates are not unique. So sometimes it got here, they both got here, but at different times, that is at different t. And so, well, that's not a big deal because you can look at it. Just plot this thing into your graphics calculator and you can totally see it reaching. It's not that big of a deal, but you need to bear in mind that sometimes you can't, making theta equal to each other may or may not yield you all the solutions of it being equal. And that is because the polar coordinates are not unique, okay? You can just keep spinning it and all that. Anyway, so that's that. And so knowing this, please do example 7.17 as part of your homework. Now in the example, once they set up the integration, then they plow through a whole bunch of integration techniques. You can do that if you feel up to it, or if you're tired, just plug it into the definite integral calculator and you'll come up with the same answer. I mean, it's so smart that it doesn't even come up with a decimal answer. It just tells you 4 pi or something like that. The only thing is, if you do plug stuff into the calculator, remember the area has 1/2 in it. So either put the 1/2 in the calculator as well by putting it inside the integration, okay? And don't leave it outside. Your calculator might not be happy or might not allow you to stick anything outside. Just don't forget to either put this in or remember to keep it later. Don't forget the 1/2. Otherwise, that's what I did, okay? I forgot the 1/2 and then I came up with the answer and the answer is, you know, too small or too big or something. And I was like, why is my answer exactly, I don't know, double of it? And it turns out I forgot to divide by 1/2. So yeah, so if you plug it into the calculator, don't forget the 1/2. Other than that, type in the limits properly and then the answer will pop right out. That way we don't wear ourselves out doing integration. We've been through integration, we've done that, we don't need to do it right now, okay? If you don't, unless you really feel like it, then that's okay too. Next, so that's for area, and next we're gonna do arc length. Now the arc length works the same as the other arc length. Let's look at the arc length for a second. Next, let's look at the arc length. The arc length is on page 667, which is, we're going to derive the arc length formula by the parametric formula for arc length, okay? And just plug the various things in, actually. So the parametric formula from the, I don't know, previous section or something that we already figured out, okay? The length is equal to dx over dt squared, dy by dt squared, take the square root, integrate it from a to b, and you're good. Now we'll plug right now we pretend that t is theta, okay? So then we are going to plug this in and plug everything in exactly as is. So the original definition of the polar coordinates states that x is r cosine theta, right? And r is f of theta. And then, so we get that, and similarly, y is r sine theta, again, r is f theta. Now, once we have that, we'll take the derivative of x with respect to theta, and that quickly use this thing here by the, what is this called? Product rule, right? And so the product rule will yield you those two formulas. Now, if you look at the formulas very carefully, I will write it down here, okay? All right, now I have written down dy by d theta, which is that thing. It'll come out quickly if you apply the product rule of the definition of y. And similarly, dx by d theta. Now this is, we're going to use this to derive the arc length formula. But before that, I want to mention that this is the same, okay, when you divide these two things, is equal to dy by dx. If you divide these things, then it equals to these two things, big long division line. See, it equals to that. Now, why do I mention that? Because dy by dx, guess what that is? That's the slope. And then in the book doesn't mention this, but you will be asked to calculate the tangent line of some polar curve. And here's how you do it, okay? So to calculate the tangent line, you need the slope. And to get the slope, you will do this part, this whole thing. Calculate dy by dx, dy by d theta, and divided by dx by d theta, and that's your tangent line at some point on your polar curve that you're asked to calculate the tangent thereof. And then you will use the Poinsot formula, as you always did in Calculus 1, to do that kind of thing. But that will be then in the homework. Your book doesn't mention it, but it does mention it in the homework, okay? So that's how you do it. Okay, now continuing, now we've done that, let's not pay attention to that and get back to our definition of dx, d theta, and so on. So we plug that in, okay, into the original formula where it equals to, let me put it this way, all right? Once you plug it in, right, so that here's your formula, like that, right here, so far so good. And then you have to plug this stuff in. Each dx is this stuff, so you plug it all in, and now you got a fairly long formula that's looking a bit threatening, okay? Now from this point on to the end, it will end up being this way. I want you to do that as part of your homework. That big long thing somehow collapsed, okay, beautifully, right? It's like a little bit of algebra magic, so that it collapsed into a nice clean thing, and I want you to figure out how that happened. And the solution is fairly obvious. So if you stare at it long enough, or just write it out, either way, okay, that will becomes this, which becomes this, which becomes this. And then you magically has a much neater formula than that big long thing there. And that is the solution, the formula for the arc length. The arc length is you integrate from one angle to the next angle, theta, right, of, well, basically r squared plus dr by d theta squared, and take the square root. Or it's also written in this form if that looks better. Either way, they're the same thing, and that's how you calculate arc length. Now that we figured out what the formula is, we're going to use it. Example 7.18. We'll find the arc length of some curve, but before that, let me repeat that please prove the theorem 7.7. Specifically, I want you to do this part, okay? The part where how the algebra come out. So example 7.18, there's a polar graph, and then you will plug it into the arc length formula, and it will give you something. What are you supposed to do here? 0.22 pi. Find the arc length of the curve. Oh, the whole thing, okay? So you need to first graph this thing to see where it ends. Because they want you to draw the whole thing, the cardioid. Well, draw the whole thing, well, just once, okay? You don't want to keep going, because then it will just keep drawing it, repeating in the same part, so you can't even see it drawing it, but you got too much, okay? We just want to know this thing one time. So go plot on the computer and see in decimals to see how much it takes to go one time. Most likely the case from 0 to 2 pi or something like that. Yeah, it depends on the cosine. But in this case, the cosine just have theta. It doesn't have 2 theta or anything like that. So it should be 0 to 2 pi. Yeah, and so once you plug in everything, you need to take the derivative, of course. That's part of the formula. So once you take the derivative and plug everything into the formula, you get right here, right? And then from this point on, the book go in detail of how to do the integration, okay? So which end up being an entire page worth of stuff. But for our purposes, if you feel like doing that, that's fine. But I recommend let's plug, instead of doing all that, let's just plug in the original thing into the definite integral calculator, 0 to 2 pi, and let that and watch the whole thing come out, okay, within a couple of seconds. Now, when you use the calculator, the definite integral calculator, you do have to pay careful attention to make sure that sometimes it gets stuck in something about negative area and the absolute value, and it might give you the wrong answer. So you have to watch out for that. And generally speaking, you just what you do is you calculate only the positive part. The negative part likely is symmetrical or something, and which is what the book is talking about here too. But the point is, watch it carefully so that the calculator didn't subtract itself out and give you some weird answer instead of the right answer. But anyways, but most of the time you plug it into the definite integral calculator and there's your answer and you're done. Okay, let's not plow through this much integration because we've been there, we've done that. We don't need to do that right now. We're just doing polar coordinates. And that marks the end of this section. So for homework, which is on page 669, please do problems 193, 197. For 197, the answer in the back is partly wrong, okay? And I'll talk about it in the when we talk about the homework. Okay, next 199, 207, 213, 17, 21, 35, 41, and 45. And when you get back, I want to talk about some of the homework. All right, now before we talk about the homework, I forgot to mention something is in this section. That is, there's something called the polar axis, which is mentioned in your homework a lot. The polar axis is their name for the x-axis. In polar coordinates, we call the x-axis the polar axis, I guess. What do you call the y-axis? I don't know. I don't notice it, so maybe you can find that out or something. But I don't think it shows up in the homework, so we're good. Okay, so the x-axis is called the polar axis, and with that, let's look at problem 193, which is r equal to 1 minus sine theta. And what are we doing here? We're supposed to come up with a formula to calculate the area of this thing. So yeah, what are we No, we're calculating the area, I think, below the x-axis only. Okay, we don't need the top part. So what you need to do is graph this thing in the Desmos calculator carefully to see which part goes where. That is, this is the top part, and the top part happens after you mess with the mess with theta a little bit. You realize the top part goes from 0 to pi, and then the bottom part goes from pi to 2 pi. And therefore, the area plugging into the formula, it goes from pi to 2 pi. Okay, that would be the integration. And that's the answer also. Next, let's look at problem 197. The 197 says that you have to draw what is this called? Limousin or something. Anyway, it has a big part and a small part. And so I will draw that thing here, I guess. Yeah, the thing looks something like this, right? You have a big part, right? Something like that. And then a small circle on the inside. And the way I understand it is they want you to calculate the area minus the circle in the middle. Well, not the circle, the loop in the middle. So I drew it out in the decimal calculator, and I figured out that the small loop is, you can do it from 5 pi over 3 to 7 pi over 3. And then the big loop goes from pi over 3 to 5 pi over 3. Yeah, and anyway, so by the time you do the area, the thing is, this is the same as you can plot the graph itself. This is 1 minus 2 cosine squared x. Okay, instead of theta, I just plotted y and x to see how the integration goes in rectangular coordinates. If you plot out the function, this is what the function looks like. So that from pi over 3, which is right here, to all the way to, where is it? To pi, which is right here, that's half of this hump. And this hump is the total area of the big object, okay? And then this part, this small hump, is the total area of the small circle right here when you do the integration. And therefore, the book made a slight mistake. The book had to start at 0. It should not start at 0. It should start at pi over 3. Because if you start at 0, then you'd be calculating the small hump and, the circle, small one and the big one, which is not correct, because we want the big one minus the small one, okay? And with that, then what happens is that we're gonna do, the book only wants to do half of it, because we're doing half, and well, you work out the dividing by 1/2, and that is the answer. We don't have to actually do the integration. We just have to figure out what the formula is. And I'm positive that the first integration should start as pi over 3 instead of 0 as stated at the back of the book. Other than that, everything is correct. Now, I have this thing plotted out, as you can see in the decimal calculator. Okay, from 0 to pi over 3 is the small circle, right? And then from pi over 3 to what is that? To pi is the big circle. You see, it started pi over 3, not 0. And that's the blue one is the top part. And you do the subtraction and multiply by, there's 2 of them, and which cancels out with 1/2 in the formula. Well, anyway, it works out that way. Look how beautiful the decimal calculator is. It makes everything look absolutely perfect, right? So anyway, so that's that. Problem 197. And yeah. So anyway, you just plug it into the area. The hard part really is to figure out exactly where the integration starts and where does it end. And you figure that out by adjusting the graph to see exactly where the starting point and the ending point is. So that's 197. Next, let's look at problem 199. I'm flipping the wrong page. There it is. Okay, problem 199, we are doing, doing this area. Okay, it's the intersection of 2 circles, identical circles that go through each other's center. Right? Diameter go through each other's center, so you get this thing that's somewhat like a football. And then we're supposed to calculate the area. We've done this before in Calculus 1, and probably before that in Algebra or something, or Geometry or whatever it is in the or Trigonometry. Anyway, we've done this many times, but we're going to do it again in polar coordinates and see how that works out. The way to do it is that we're going to cut this area into 2 parts. First, we are going to do the set A1. A1 includes both sides, but they're the same, so we're only going to calculate probably half of it, or something. Or not. I don't know. Anyway, so A1 is going from, is the sector, that is the fat slice of pie. And then A2 is that tiny area, see, the thin slip thing right here, that little bit, okay? And that part is integrating from, A2 is integrating from 0 to whatever angle is that meets the intersection point, this one. So then when you do the integration, then the area, when you do this thing, then the area equals to something that is correct. Yeah, the answer at the back gives a different presentation. I don't know why, but it doesn't make any difference. The answer is the same. And the answer in the back somehow came up with cosine. I'm not sure why they're doing cosine, because the formulas, the problem given to us as sine, right? It says r equal to 4 sine theta. So I'm not sure why they're integrating cosines, but the answer is the same, so we're good. Next. Problem 213, we have 2 curves which encloses themselves into some shape, okay, and we're supposed to calculate the area. Now the area is, we'll calculate it in 2 parts. That is the left side and the right side, and then figure out where the angle is that does that, okay? If you adjust these 2 graphs in the decimals, the graphics calculator, you will quickly find out that the one side is from pi over 2 to pi, while the other side is from 0 to pi over 2. So then you plug into the area formula. Don't forget the 1/2 here, see? And then add it up. Again, don't forget the 1/2, and then you come up with the right answer. The integration, I just did the integration in the calculator. I cannot be bothered to do integration now. Let's not bother. Okay, so that's 213. Next, I need to do 200, what is that? 217. There's nothing to say about 217, really. I will show it to you since I already did it, but yeah, there's nothing worth mentioning. And next, 221, here is, what are we doing here? I think this is probably the arc length. Yeah, and the arc length is slightly simpler because for the area, you often have to determine where are we integrating, what are the limits, where's the arc length. They have to tell you exactly most of the time, right? Unless they're talking about the whole thing, and then you have to figure out how long, what it takes the angle to go through at one time. But this is not the whole thing. They just want part of it. So then we'll plug it into the formula, which is kind of hard to integrate. I don't know. And instead of working on that thing to make it happen, we'll just plug it into the definite integral calculator, and here's your answer. And that is marks the end of this section.